Hi, everybody, and welcome to Chapter 2, Section 8, Curve Sketching. And we're going to start out with this definition. I know definitions are really hard to read, so as we read, we're going to draw a picture which will really help understand what it means. So first it says the function is increasing on this interval AB. So let's say I have a graph, and here's A, and here's B, because that means it's an interval. And also it's telling me that A is less than B. But there's these two other values between them, x1 and x2. And x2 is bigger than x1. It implies that y1, or the function at x1, is less than the function at x2. Well, if we have a point here at x1, and it has to be, the y value has to be smaller, let's say this is the next one at x2, it's increasing because the y value is getting bigger. And the same is true if I did the opposite, that everything's exactly the same, but now it says it's decreasing if on this interval y1 is bigger than y2. Let's call this f of x1, and we'll call this f of x2. x1 is greater than x2. So we can see that it's coming down or decreasing. The same ideas make sense if we consider h of t to be the height in feet of a rocket at time t seconds. We naturally say the rocket is rising, or that its height is increasing, if the height increases over a period of time as t increases. The rocket's going up. As long as it's going up, it's increasing. Example 1. List the interval on which the function shown increasing or decreasing. It's increasing here. It then starts to decrease. Right around here, it starts to increase. It's increasing here to here. So yellow is increasing. Let's say green is decreasing. So where is it decreasing? Well, from here to here, it's decreasing. And from here to here, it's decreasing. And what it's doing when it's flat is it's constant. So if I'm trying to find my intervals where it's increasing or decreasing, I have my interval where it's increasing would be from everywhere that's yellow, because I said yellow is increasing. So 0 to 0.5, comma, 2 to 3, and 4 to 6. It's increasing everywhere I put yellow. It's decreasing everywhere it's green. I guess I got those mixed up. So from 0.5 to 2, it's decreasing. And from 6 to 8, it's decreasing. And the last thing, we can say it's constant. From 3 to 4. Even though it doesn't ask me for that, I can see that from the graph. That's how it looks. And notice I always put open brackets, always put parentheses, because I can't have it increasing and decreasing at 0.5. It's got to be one or the other. So I just say, we'll call 0.5 the point of transition, where it transitions from increasing to decreasing, and we don't include that anywhere. Number 2. Now we're going to talk about the first derivative and what we can use the first derivative for to find the shape of a graph. So we start here. It says, for a function f, which is is differentiable on an interval. So we have a function, we may not be able to find the derivative everywhere, but as long as on an interval that we pick, we can find the derivative, then that's what we're talking about. One, if f is increasing on AB, then the derivative is going to be greater than 0. If f is decreasing on the interval AB, then the derivative is going to be negative. And then if the derivative equals 0, it's going to be constant or flat. Example 1. The graph shows the height of a helicopter during a period of time. Sketch the graph of the upward velocity of the helicopter, which they're asking for the dH dt. Now, the first thing I want to do is time versus velocity, because the velocity is going to be the first derivative of the height. Step 1 is to find the place where the slope equals 0. You can say where the tangent line is horizontal. And that always occurs at maximum and minimum points, local max and mins. Here's a maximum, a local maximum. Here's a local minimum. Here's a local maximum. My tangent line is horizontal, meaning the slope is 0, which means if I'm graphing the derivative at 2, my derivative graph, or h prime of t, is 0. Also at 3, it's 0. And also at 5, it's 0. So I know my graph is going to go through those points. Also, I know that it's positive. Here I have different intervals. I have an interval from 0 to 2. It's increasing. Let's just do all the increasing. 0 to 2, 3 to 5, and that's all my increasing. My decreasing is from 2 to 3 and from 6 to 7. That means my derivative is going to be greater than 0 here, and my derivative is going to be less than 0 there. And we already know what's going to happen at the point is going to be equal to 0. Now, if I put this ruler and make this the tangent line, notice it starts out about like this, but as I get up to the top, it's slowly changing the slope until it's 0. But it's always positive. It's always positive, but it's getting smaller and smaller. So it starts out at a positive value, whatever my slope is here. But as I go up, notice the slope is getting smaller until it gets to 0. But all those values are positive. The slope of that is negative, but the values are all positive. From 2 to 3, it's negative, which means it's going below this line. From here to here, it's negative. So it's got to go under the x-axis or t-axis. Then it's coming back up, and it's coming up at a pretty decent pace. It gets bigger, and it comes here, it starts going up, and then it comes back to 0, because at 5, it's 0. Now, I don't know exactly what it looks like. I know it looks something like that. Down here, I have a graph of what it's really looking like. And you can see it's positive, and it's getting closer and closer to 0. Mine's positive and getting closer and closer to 0. I just don't have I don't have good enough values to make that turn. Between 2 and 3, it's negative, which is what I said. From 3 to 5, it's positive, and then it becomes negative. So this is my f prime of t, This is the actual f prime of t. Or h prime of t, excuse me. For a function f, which is differentiable on an interval I, the first thing I want to do is find the derivative. F prime of x is equal to 3x squared minus 12x plus 9. And if I want to graph the derivative, I want to graph the original function, but I know something about the derivative. If I set this equal to 0, I'm going to find my maximum and minimums, also called my critical points. My critical points are when the derivative is equal to 0 or the derivative is undefined. When it's equal to 0, it's a max or a min. I can factor this. Let's factor out the 3. We get x squared minus 4x plus 3, which equals 3 times x minus 3 times x minus 1 equals 0. I have a 0 at x equals 3 and x equals 1, which are my critical points. And there's no place where it's undefined. So I start off, and I know since I have a 0 at 1 and 3, I have maximum and minimum values. How do I know if I have a maximum value? How do I know if I have a minimum value? I can put it on a number line. So if I have a number line, and this is 1, and this is 3, I know I have zeros here. And when x, there's two different ways you could do this. I'll do it the way most people do it, and then I'll do it the way I like to do it. I have these 3 different intervals. I want to know what happens on negative infinity to 1 interval. I want to know what happens on 1 to 3 interval, and I want to know what happens on 3 to infinity interval. So from negative infinity to 1, everything is the same, nothing's changing. Let's put in 0, because that's obviously the easiest one. If I put 0 in for my derivative, when x equals 0, f prime of 0 is equal to 9, which is positive. That means from all of this, my derivative is positive. Here I can put in 2. Between 1 and 3, I can put in 2. When x equals 2, f prime of 2, we plug 2 into the derivative, so f prime of 2 is equal to 3 times 2 squared minus 12 times 2 plus 9, which is equal to 4. This is 12 minus 24 plus 9, which is equal to negative 3. I don't care what the number is. I just want to know it's negative between 1 and 3. And then if it's greater than 3, I could say f prime of 4. I'm going to have a positive number. Trust me. It's going to be positive. So that's one way to do it. You can use that number line method. Here's the method I prefer. When the function equals 0, I have my zeros. So I know that I have a 0 at 3 and a 0 at 1. And I also know that when it's less than 1, I have 3 times a negative number times a negative number, which equals a positive number, which makes this positive. When x equals 2, I have 3 times, and I'm looking right here. So when it's 2, x minus 3 is negative, but 2 minus 1 is positive, which gives me a negative value. So between 1 and 2 is negative. I don't really care what the number is. All I care is if it's positive or negative. And then when x is 4, I can say I have 3 times 4 minus 3, which is 1, times 4 minus 1, which is 3, which is a positive value. So I know this interval is positive. Now I know it is increasing from negative infinity to 1 and from 3 to positive infinity, and it's decreasing from 1 to 3. I learned all that just from using the derivative of my function. I want to know if 1 is a max or a min. When x equals 1, do I have a maximum or a minimum? Well, if I have a positive slope to a negative slope, I'm going to have a maximum value. So I know when x is 1, that's my maximum. And when x equals 3, do I have a max or min? Well, I'm going from a negative slope to a positive slope. So notice I'll have a minimum. So when x equals 3, I have a minimum value. I can say this graph, it's going to look like this. And I can find my maximum value. And I can find my minimum value. All I have to do is plug it into the original function. So when x is 1, I plug it into f of x, which is right here up at the top. So when x is 1, I have 1 minus 6 plus 9 plus 1, which equals negative 5 plus 9 is 4, plus 1 is 5. So my maximum value is 5. And I have that 1 point. So now I know this is 5. That's how high it goes. And I know my minimum is 3. So I can plug in 3 here. And I have 3 to the third minus 6 times 3 squared plus 9 times 3 plus 1, which equals 27 minus 9 times 6, 54, plus 9 times 3, which is 27, plus 1. 27 plus 27 is 54. 54 minus 54 is 0, so this equals 1. My minimum value is 3, 1. We can adjust it. I have a point, 1, 5, and I have another point, 3, 1. That's my max, that's my min. So my graph is going to go like this, and like this. And I can plug in more values, but that's basically what my graph is going to look like. I can plug in x equals 0, and I have 1. Oh, look, it went through 1. So this is a pretty good graph. So here we have increasing, decreasing, increasing from negative infinity to 1, from 1 to 3, and from 3 to, yeah, it's infinity. We don't have an end point. And so this creates, if I were to connect these dots, these lines, notice it has a similar shape to our function. It's just that we don't know where the values are from here. Second derivative. So until now, we've used only used the first derivative information, but we also get some information from the second derivative. And it gives us more information into the shape of the function. So the second derivative, if the second derivative is greater than 0 on some interval, we know it's concave up. Concave up means that if my second derivative is greater than 0, my graph is concave up. If my second derivative is less than 0, my graph is concave down. that doesn't really show you everything, because it could be positive and concave up, or it could be positive and concave down. Both of these have a slope is greater than 0 because they're both increasing. But for this one, the second derivative is greater than 0 because it's concave up, and here it's concave down. So f double prime of x is less than 0. The converse is true. If the second derivative is greater than 0, then we know it's concave down. So it's true in both directions, basically. And we can use that information to determine things about our graph. First thing I'm going to do is I'm going to take my first derivative. F prime of x equals 3x squared minus 12x plus 9. And again, we know we can factor this to x minus 3 times x minus 1. The second derivative is equal to the derivative of the first derivative, which makes it 6x minus 12. And I can factor this to 6 times x minus 2. For this one, we figured out that we have a 0 at 1 and a 0 at 3, and it's increasing from here to here. It's decreasing from here to here, and it's increasing after that. That's the first derivative. Now let's look at the second derivative. The second derivative, I have my 0 at x equals 2. The second derivative equals 0. This is called my point of inflection. My point of inflection is where the graph changes from concave up to concave down. Because it's 0. When x is less than 2, this is going to be negative. When x is less than 2, x minus 2 is less than 0. That means this is decreasing or negative. When x is greater than 2, x minus 2 is greater than 0. So this is concave up. Now, if we want to put it together, we can go look back at our graph, which we said looked like this. I know that it's increasing from negative infinity to 1, and it's decreasing from 1 to 3, and it's increasing from 3 to infinity. I know that from my first derivative. At x equals 2, this is changing. That's my point of inflection. I can say all this is concave down, but starting right here, it goes into being concave up because of this being negative and this being positive. And that's really us putting it all together.